Each class. Today we will see the first chapter, which is solutions. So in this chapter we will cover the part which deals with the concentration terms. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the same. What is the objective of this lecture? So as I told you, we will study about different type of solutions. First of all, depending upon the states. And second thing, how we can signify, or we would say how we can represent this solution's concentration in different units. Then if I come to the topics, specifically, we will first see the introduction of this chapter, solution. Then we will see the type of solution. Then after that, expressing concentration of solution and the examples and the in-text question related to these three topics. First, we will start with the homogeneous mixture. Now, why I am saying a homogeneous mixture? Because every solution, in fact, the solution word means itself that the mixture is homogeneous. Homogeneous means the composition and the properties, both of this are uniform or same throughout the solution or the mixture. Now, if I talk about the components of this homogeneous mixture, say our solution, then the first obvious component is solvent, the component which is present in the largest quantity, and you can say almost all the properties, whether the physical and chemical properties, are well defined with this solvent only, because solvent is the dominant one. Now, rest of the components whose concentration is less as compared to the solvent's concentration are studied under this solutes. Now, there can be 1, 2 or many more solutes, but here we will specifically deal with binary solution. Binary solution means one solvent and one solute. So remember this thing. What are we dealing with? We are dealing with a solution, and solution is a homogeneous mixture, and specifically we are dealing with the binary solution where we have one solvent and one solute. So this was the overall view of the chapter. Now we will see various types of solution depending upon their states. First one is gaseous, second is liquid solution, and third one is solid solution. Now I have told you in the start that the state of the solution is mostly decided by the solvent, and as you can see here that if your solvent is gas in these three cases, then your state of solution is also gaseous. Similar to that, if the solvent state is liquid, our solution is in the liquid state, and if our solvent state is solid, our solution is in the solid state. Now we can mix different solutes of different states in this gaseous, solid or liquid solvent. Starting from the first one, we have solute as gas, liquid and solid in the gas. So if I talk about the gas in gas, it is seen everywhere. So the atmosphere that you observe is nothing but a mixture of different gases. Like we can take it for the oxygen and nitrogen. If you take a mixture of oxygen and nitrogen, so it will be a binary solution and a gas in a gas type of solution. Then coming on to the next type of solution, which is liquid gas, where liquid is the solute and gas is the solvent. So in this type, we have chloroform mixed in the nitrogen gas. Moving on to the last gaseous solution, which is a very common example. So if you are dissolving solid in a gas, which is camphor in the nitrogen gas, we said that your solution is solid in gas. How we can do it? It's very simple. Just take camphor, put it in a nitrogenous environment. We know it very well that camphor slowly sublimes and gets converted into gaseous state directly, and that will result in a mixture of solid and gas. Coming on to the next type of solution, liquid solution. So if you are dissolving gas in a liquid, we have an example of oxygen dissolved in water. Then you can also take the example of carbon dioxide dissolved in water in your soft drinks. After that, we have liquid in liquid. So it's a very easy example to think of. You can take the example of ethanol dissolved in water or milk dissolved in water. So I will put you a question. So if you take oil in water, is it a solution? No, it is not a solution because they don't mix uniformly, as their polarity nature is completely reversed. So it is not a solution of a liquid type. Then solid in a liquid, you can take the example of sugar in water. You can take the example of salt in water. Here we have taken example of glucose dissolved in water. Our last type is solid solution, in which we dissolve gas, liquid and solid onto the solid. So first, if we dissolve gas onto the solid, so we can think of the example of hydrogen on palladium. Now, you are familiar with this kind of solution. You must have seen the reduction. In the reduction part of alkene, we take hydrogen gas adsorbed on this solid surface, which ultimately results in reduction of alkene. So that example is put up here. Then moving on to the liquid solid. So we can take the example of amalgam of mercury with sodium. And lastly, solid, for which we have the variety of alloys that we see. So every alloy that you see is an example of solid, like copper dissolved in gold. Or you can think of the example if you take the heater and look at its coil and study its composition, then you will find that it is made up of various type of materials. Now, why do we do so? To gain some specific properties, because your coil needs resistance. At the same time, it needs conductivity somewhat, and it should be stubborn so that it doesn't get melts away. Is it clear? So these are the three types of solution. Then what are the ways we can represent this concentration? So you need the concentration part, or else it will be very difficult to conduct any experiment related to this solution. Starting with the first one is the mass percentage. Mass percentage is very simple. If you have a solution, then your every component will have some percentage mass contribution to the overall solution. That thing is simply called your mass percentage. So here is your formula. Suppose you are trying to calculate the mass percentage of a component. You will simply put the mass of that component divided by the total mass of the solution in which your component was present, multiplied by 100. Now it's very easy to imagine. It is very similar to the percentage of mass that you see. Similar to that, total mass by the mass of the component. Okay. So total mass will be in the denominator and the mass of the component will be in the numerator. Talking about the example. So examples are very important here. Why? I will let you know. For this, you should imagine a 10% glucose in water. Now, what does it mean? It means that if the total mass of the solution is 100 gram, then 10 gram is glucose. Okay. And the rest of the part, which is 90 gram of obviously, is your water. Now, you should always think in this way, and this will be very helpful in solving the numericals. What is the use of this? So it is commonly used in the industrial chemical application. Example, if I talk about the commercial bleaching solution, it contains 3.6 mass percentage of sodium hypochlorite in water. Means if you take 100 gram of this commercial bleaching solution, then in that 3.62 grams will be of sodium hypochlorite. I hope you are getting the point here. It's very simple to think of. Just think it of as a simple percentage in terms of masses. Then, similar to the mass part, we have a volume part, where we take the volume of the component divided by the total volume of solution. This will give you your volume percent multiplied by 100. Yeah, 100 is obviously important to convert it into percentage. Now again, think of an example. take a 10% ethanol solution in water, which means we have 100 ml of solution in which 10 ml of ethanol is present. Okay, and the rest of is present as water. Now remember that this water 90 ml part is taken because we are considering that we have only ethanol and water in the solution. It's a simply binary solution. What is the use of this? So again, if you have an anti-freezant, what it does, it lowers the freezing point of water. And this thing is used in cars for cooling the engine. The solution that we take here is that 35% volume by volume of ethylene in glycol, okay, in water. And here you will see that the freezing point of water goes from 0 degrees Celsius to minus 17.6 degrees Celsius, and this is a very large dip in the freezing point. So what it does, again I am repeating, it lowers the freezing point of water. Why I am repeating it? Because this thing will be noticed further in the colligative property, which is termed as lowering of what? Lowering of melting. Clear? Then we can take a combination of mass and volume, but here your units will be fixed. Suppose we are saying that weight by volume, then what will be the unit of volume? Suppose we are taking 100 ml. In terms of ml we are taking. And your weight will be in the gram. So this thing will be mentioned that if it is mass by volume, then what is the unit of mass and what is the unit of volume? And again that thing will be multiplied by 100. Coming on to a very interesting concentration term in which most of the students find difficulty. What is that? So it's very simple to think of. What we do initially, what we have done initially, I would say, is we have taken 100 as the multiplying factor. Here we have taken 10 to the power 6. And the rest of the fraction, which is number of parts of the component by total number of parts of all components of the solution, this part can be described in terms of mass, in terms of volume. So suppose you can take, suppose if you have 90 ml of the solution, or else you can take 10 ml of the 100 ml of the solution, in which we have 10 ml as the solute and 90 ml as the solvent. Then what is the parts per million of the solute? It will be 10 by 100 multiplied by 10 to the power 6. Now, why are we doing this? This is important. We have already the percentage part and we are just multiplying it with a large factor of 10 to the power 6. We will see why we have done it in the next slide. So the thing here is that in some cases, the concentration of the component in which we are interested is very, very, very less. And in that case, we have to deal with a large amount of decimal places. Okay. So what we do? We take a wholesome amount of solvent. Okay. And then we can represent it easily. Suppose in 100 grams, we have 0.0001. So I have told 3 times 0. If I increase the volume of that same solvent by a large factor, then the amount of solute will be now less in decimals. Okay. So you're simply multiplying the concentration by 10 to the power 6 to remove the, you can say, difficulty of decimal. Now, let us take an example of that. So here is an example. If you take 1 liter of seawater whose weight is 1030 gram, it contains only 6 into 10 to the power minus 3 gram of oxygen. Now this amount is very less as compared to your initial water amount. Now it makes very difficult to remember this value. So what we do is we take 10 to the power 6 as the multiplying factor. So we have multiplied by 10 to the power 6. Okay. And we got 5.8 gram per 10 to the power 6 gram of the seawater. Clear? Then our new concentration will be 5.8 ppm. Remember, the mass of the solute is taken as gram and the mass of the solution is also taken in gram, and then we have multiplied the same thing with 10 to the power 6, and then we have got this 5.8 ppm. Similarly, your concentration of pollutants is expressed in terms of mu grams per ml, where mu gram is simply 10 to the power minus 6 gram, or ppm, you can say it also as ppm. We will do questions on it which will make it more clear to you. Coming on to the next concentration factor, which is mole fraction. Now this concentration term is more meaningful for the gaseous element, as their volume is very difficult to define, but the moles are always fixed. This mole fraction is represented by the symbol chi. Suppose we are trying to calculate the mole fraction of a component, then what we do? We take the number of moles of the component whose mole fraction we are trying to calculate divided by the total number of moles of the solvent. In case of a binary mixture, suppose a binary mixture has A and B only, and Na and Nb are the number of moles of A and B. Then what will be the mole fraction of A? We will write it with the help of chi A. So here A is in the subscript and chi is written in the normal form, is equals to number of moles of A by total number of moles, which is Na plus Nb, as we have a binary solution which contains A and B only. Now, after all, it is a fraction. If you add all the fraction, it will give you one. Take the example of a cake, just cut it into 6 parts. Okay. Now, if you add each fraction of this your cake and make it a whole, then it will be obviously equals to 1. So that same thing is implied with the help of this notation. So suppose ith component has a mole fraction written in this way: number of moles of I by total number of moles. So we have done a summation for n1 to ni. So this summation means we are adding n1, n2, n3, and n4 up till ni. Then similarly, you can do it for chi1, chi2, chi3, chi4. Okay, you will get the mole fraction of the first component, the second component, and suppose there are ith number of component, then you can get it for the ith number of component. Add all of these mole fraction, you will get your final value as 1. So mole fraction is related mainly to the vapor phase, as I have told you, and it is quite useful in describing the calculation which are involved with gaseous mixtures. We will do the first question now. In this, we have to calculate the mole fraction of ethylene glycol, whose formula is C2H6O2, and we have taken 20% by mass solution. Okay, very simple to solve. Let's see how we can do it. We have to calculate the mole fraction whose 20% mass by mass concentration is given already. So first of all, if we are saying that 20% C2H6O2, it means that 100 gram of the solution will contain how much? 20 gram of this ethylene glycol. We have seen this terminology previously. And what will be the mass of water? It will be 80 gram, the remaining part. Then we were interested in the mole fraction, so we have to calculate the moles. First, for ethylene glycol, we have to calculate the moles. So for that, we have calculated the molar mass initially: 12 into 2, 1 into 6 for hydrogen, and 16 into 2 for oxygen. Add all of this, you will get the molar mass as 62 gram per mole. Then the moles of this ethylene glycol will be 20 gram divided by the molar mass. Means given mass, which is 20 gram, divided by the molar mass. This will give you 0.322 as the number of moles of C2H6O2. Now, we are interested in the number of moles of water. Then we will add the total number of moles. Okay, for mole fraction, we need the number of moles of ethylene glycol divided by the total number of moles. We have calculated for ethylene glycol. Now we will calculate the total moles. So we have 80 gram of water and the molar mass of water is 18 gram. That gives you the moles of water as 4.44. Again, I am repeating the formula for moles, given mass by molar mass. So we have seen that 80 gram of water contains 20 gram of ethylene glycol. So we have the mass of water, we have the mass of ethylene glycol, and we have their moles also. So we can write the mole fraction of the glycol as moles of your ethylene glycol by total number of moles. We are adding both of this, 0.322 by 0.322 plus 4.444. That calculation will give you mole fraction as 0.068. Similarly, you can go and calculate it for the water also, and you will get 0.932 as the mole fraction. Else, you can take a shortcut, and that shortcut lies in our fraction thing, that adding all the fraction will give you 1. So we have only two components here, ethylene glycol and your water. So if you add both of these mole fractions, you will get 1. So with that analogy, we can calculate the mole fraction of water as 1 minus 0.068. So initially we have calculated 0.068. Okay. Here in the ethylene glycol, you will get the mole fraction of water as 0.932. So we have to now look at molarity. So next question, not next topic, which is molarity. So what is molarity? It is number of moles of solute dissolved in 1 liter of water. And that 1 liter should be always fixed, because molarity means moles divided by the volume of solution in liter. So the volume should always be in liter. And when you put 1 liter, you can also put 1 decimeter cube or 1 cubic decimeter. So remember that 1 liter is equals to 1 decimeter cube. For example, if we are taking a molar solution, 0.025 molar solution of NaOH, or you can write it as mole per liter also. Here is a very important symbol for it. So molarity is has also a unit of capital M. So you can write capital M in place of mole per liter. So if you have a 0.25 molar solution of NaOH, that means that 0.25 mole of NaOH is dissolved in 1 liter of the solution, or 1 cubic decimeter of the solution. That same analogy we have seen in the mass thing. Okay, we have used it here also, and it helps you to make the calculation easier. You have seen it just now. Our next question will be related to this molarity only, where we have the mass of NaOH given and the volume of the solution as 450 ml. So how we will solve it? Moles of NaOH will be given by 5 gram by 40 gram. Why we have written here 40 gram? Because 40 gram per mole is the molar mass of sodium hydroxide. Just add 23 plus 16 plus 1. Okay, you will get here 40. Then given mass by molar mass, same formula. There is no change in it. And remember, your mass should be in gram to calculate the molar mass. Okay, to put it with the molar mass. So this will give you 0.125 as the number of moles of sodium hydroxide. Then to calculate the volume, we have converted this thing into liter, because our molarity definition says that it is number of moles per liter of solution. For that, we have converted it by dividing by 1000. So 450 by 1000. Now putting all of these values, that is moles and your volume, in molarity formula will give you 0.278 m as the molarity. Again, we have used the capital M instead of mole per liter as the unit. You can do it. or we can write it mole per liter also. And one more way would be per decimeter cube also. So these three ways can be used to write the molarity. Okay, so these three ways are very, very important. Either capital M, which simply says 0.278 molar, 0.278 mole per liter, or 0.278 mole per decimeter cube. All these are same. Then we have molality. Its definition is moles of solute that is present in per kg of the solvent. Again here, the mass of the solvent is taken, and that should also be in kg and not any other mass unit. So suppose if we have a solution whose molality is 1 mole per kg, it means that 1 mole of KCl, suppose we have taken the KCl solution, so 1 mole of KCl is present in 1 kg of water, and 1 mole of KCl has 74.5 gram of KCl. And this thing will be present in 1 kg of water. Now we have seen various type of concentration term, and each concentration term has its own merits and demerits. Some will be used in case of gas, some will be used in case of solution. But an important thing is that your mass percentage, ppm, mole fraction and molarity, all of these are independent of temperature, but your molarity depends upon temperature, as the volume will change upon change of temperature, but not your mass. Mass will be same. Okay, mass is you can say mass is conserved, but volume is not under the law of conservation, so it will change depending upon the temperature, and due to that the molarity is also a function of temperature. Now let us see questions on it. You have to calculate the molality of 2.5 gram of ethanoic acid in 75 gram of benzene. So benzene is your solvent and 2.5 gram ethanoic acid is your solute. How you will calculate this? To calculate this, you must use all the data that is given here. With the help of the formula and plus this data, you can solve it very easily. First, we will calculate the number of moles of ethanoic acid, because formula says number of moles of solute divided by mass of solvent in kg. For that, we have calculated the molar mass. It comes out to be 60 gram per mole. Then number of moles is calculated by dividing given mass by molar mass, which is equals to 0.0417 mole. What is the mass of benzene in kg? We are given the mass in gram, so divide this 75 gram by 1000 to convert it into kg. It will give you 75 into 10 to the power minus 3 kg. Then molality is equals to moles of ethanoic acid by mass of benzene in kg. So 0.0417 by 75, and on the upside we have this 1000. Upon calculating this, you will get it as 0.556 mole per kg, or you can write here small m also in place of this mole per kg. So this thing, small m, is used in the same way as the capital M is used for molarity. Our next question is saying that mass percentage of benzene and carbon tetrachloride is to be calculated if you are having 22 gram of benzene dissolved in 122 gram of carbon tetrachloride. A very easy question to solve. Let's see how we can do it. So for that, we have taken the mass of C6H6 divided by the total mass of the solution. It's very obvious. We are calculating the mass percentage of this benzene. So we have taken the mass of benzene by total mass of the solution multiplied by 100. What is the mass of benzene? It is given here. It is 122 for carbon tetrachloride, and for benzene it is 22 gram. So 22 by total mass. Total mass is 22 plus 122, which is your total mass of the solution multiplied by 100. It will give you 15.28%. Then the mass percentage of the CCl4 can be calculated in the same way. mass of the CCl4 by total mass of the solution. This will give you 84.72. You can just look at the calculations. It's very easy. 122 by 22 plus 122. Same thing. We have just replaced the mass of benzene with the mass of carbon tetrachloride. But we can do the same thing in an alternate manner also. How? Subtract this thing from 100 and that will give you the percentage of carbon tetrachloride as your solution is binary. So kind of same thing we have done it with the mole fraction, where we have subtracted it from the 1. Here we are subtracting it from the 100 because we are taking 100 part of it or the percentage part of it. Moving on to the next question. It is saying that the mole fraction of benzene in solution of 35% mass by mass, okay, in carbon tetrachloride. We have already seen this type of question, so you don't have to hang upon now. You can easily solve it. First, by saying that 30% mass in carbon tetrachloride, what do we mean? We mean that if we take 100 gram of solution, we have 30 gram of benzene present in that. Similarly, the mass of carbon tetrachloride will be 100 minus 30. Then further, we have calculated the molar mass of benzene here. So this is coming out to be 70 for carbon tetrachloride, and molar mass of benzene, if you calculate, so it is 12 into 6 for carbon and 6 into 1 for hydrogen, which is 78 gram per mole. So number of moles of benzene would be given mass by molar mass 30 by 78. 30 was the molar given mass of benzene, as we have 30% by mass solution. If you divide it, you will get it as 0.3846 mole. Then what is the molar mass of carbon tetrachloride? 1 into 12 for carbon and 4 into 35.5 for chlorine, as there are 4 count of this chlorine atom. If you add this, you will get it as 154 gram per mole. Then the number of mole is 70 by 154 because 70 gram is present as carbon tetrachloride. This will give you 0.4545 moles. Coming on to the formula of mole fraction for benzene, it will be number of moles of benzene by total number of moles, which includes benzene plus carbon tetrachloride. Now 0.3846 was your number of moles of what? This benzene, and we have calculated here for the carbon tetrachloride as 0.4545. Put in this formula, you will get the mole fraction as 0.458. Then our next question. Here we have to calculate the molarity of each of the following solution. First is 30 gram of cobalt nitrate N plus 0.6H2O in 4.3 liter of solution. Then 30 milliliter of 0.5 molar sulfuric acid in 500 ml. Okay, it is diluted to 500 ml. So these are the two situations. So let's see how we can solve it. So molarity is given by the formula moles of solute divided by the volume of solution in liter. So we need the moles of solute first of all. For A, we have cobalt nitrate 0.6H2O. Okay, so that will count up to 6 into 18 for water and rest of this for the cobalt nitrate. That will give you molar mass as 291 gram per mole. What is the moles of now cobalt nitrate, hydrated cobalt nitrate? It is 30 by 291 because 30 gram of cobalt nitrate has been taken. So to calculate the molarity, we will take the number of moles divided by the total volume, which is 4.3 liter. Now coming on to the next part. So for the first, we have calculated it, the fraction we have given earlier. For the second case, what we are doing is we are taking 1000 ml of 0.5 molar H2SO4. It is given here, right? Why we are saying that? Because the molarity is 0.5. That means 0.5 moles of this H2SO4 is present in 1000 ml. Okay. Further, if you know this, how we can calculate mole? So your formula is molarity is equals to number of moles by volume. So number of moles is equal to molarity into volume. So this is your molarity 0.5 and your volume, since we are getting 1000 ml here, so we are converting this thing into what? Into liter. Okay. So 30 ml by 1000. See, it is written 30 ml. So we are converting it into liter. This will give you the number of moles. Now you are dissolving this same number of moles in 500 ml. You got my point, right? So when we are diluting this thing from 30 ml to 50 ml, we are not changing the number of moles of H2SO4. So for the first case, we have calculated the number of moles by simply using the formula M1V1. Before that, we have converted the volume into liter. So this will give you the number of moles. Then the new volume is 500 ml. So we divide the number of moles by 0.5 liter to give you 0.03 molar solution as your molarity. Then our next question. We have to calculate the mass of urea whose formula is NH2CONH2 required in making 2.5 kg of 0.25 molar aqueous solution. How will solve it? So we have to take 2.5 kg of this 0.25 molar aqueous solution. What is the mass that is present in that? First, initially, we will calculate the number of moles. Before that, we have to know the molar mass. Molar mass is calculated by using the formula, which is simply the number of, say, stoichiometric coefficient multiplied by the molar mass. That will give you the 60 gram per mole as the molar mass of the urea. Then, if we are saying that we have 0.25 molar aqueous solution, which means 1000 gram of water contains 0.25 moles of urea. Okay. And 0.25 means how much mass? So simply multiply the moles by given mass. This is the formula, because if you want to calculate the mass, you will simply multiply the molar mass into what? Molar mass into number of moles. So molar mass is 60 multiplied by 0.25, which will give you 15 gram of urea. So in 1000 gram, we have 15 gram of urea. But we have to calculate it for how much? We have to calculate it for 1000 plus 15 gram of solution. 1000 plus 15 gram of solution. So that will make you the gram as 15 into 2500 by 1000 plus 15, which is equal to 36.95 grams. I hope you're getting the point here. Now, this is approximately equals to 37 gram of urea. So the mass of urea which is required is 37 gram. Moving on to the next question. You have to calculate the molality, and the mole fraction of Ki. If the density of 20 mass by mass aqueous Ki is 1.202 gram per ml. So it's an easy question. You just have to know one formula, which is density is formula, mass per unit volume. Let's see how we can do it. So you are given the mass by mass percentage, which is 20, and your density is 1.202. So these are the three things we have to calculate. First, we will focus on molality. So to calculate molality, we have to know the molar mass of Ki. So 39 plus 127 will give you 166 gram per mole. If we are saying 20 mass by mass percent means 20 gram of Ki is present in 100 gram of solution, or 20 gram of solution, 20 gram of Ki is present in 80 gram of water. Okay. Is this thing true? Yes, it is very true, because in 100 gram we have 20 gram of Ki and rest of this is water. We are interested in the molarity. How we'll do it? First, we'll calculate the number of moles of Ki. For that, we must know the molar mass. Okay. So, moles of Ki will be given mass 20 by molar mass 166, which we have calculated it in the previous section. Then mass of water is taken in kg. So, instead of writing 80, we have written it as 0.08 kg, because 80 was in the terms of gram. If you do this whole calculation, you will get it approximately as 1.51 molar solution. Now we are interested in the molarity part. It is already given that the density of the solution is 1.202 gram per ml. First, we convert this thing into milliliter. How we are converting? Because we know the density. So volume will be what? Density is mass per unit volume. So volume will be density by mass. Okay. So it is written here. So it is mass by density. So mass is 100 gram and density is 1.202. It will give you 83.91 milliliter. But for molarity, we need the volume in liter. So we have multiplied the same thing by 10 to the power minus 3. After that, what we have done is we have calculated the molarity. For that, we need the number of moles, which is 20 by 166. We have done it already. Divided by the volume, which we have calculated it as 83.91. So here we are calculating the molarity. In this part, we are calculating the molarity. Molarity will be 1.45 molar. Last thing we are interested in is your mole fraction. We need the number of moles for both of the component. Moles of Ki will be 20 by 166. We are doing it from the start, which will give you 0.12. And moles of water will be mass of water in gram, 80 gram, divided by the molar mass. This thing will be equal to 4.44 mole. If you want to know the mole fraction of Ki, what it will be? It will be moles of Ki divided by the total number of moles. So 0.12 by 0.12 plus 4.44. It's very easy to see how we have done it. Then this calculation will give you 0.0263 as the mole fraction of Ki. So with this, we have calculated all of these three parts. So thank you for attending this lecture.